In this example, we learn how to use a power series expansion of x of z. This expansion helps us see the values of x of n in the time domain. The z transform can be written as a long sum. Each term has a number and a power of z. Each power tells us which time index the value belongs to. In this case, x of z looks like this. It has 4 times z squared plus 2 plus 3 times z to the minus 1. This means the signal has 3 non-zero samples. 4 times z squared means x at n equals minus 2 is equal to 4. 2 means x at n equals 0 is equal to 2. 3 times z to the minus 1 means x at n equals 1 is equals to 3. All other values of x of n are 0. So the impulse property says this: a shifted delta in time has a power of z in the z domain. For example, delta at n plus 2 maps to z squared. Delta at n maps to 1. Delta at n minus 1 maps to z to the minus 1. So we can write the signal x of n using impulses. These impulses match the powers in x of z. Z squared matches the sample at n equals minus 2. The constant term matches the sample at n equals 0, and z to the minus 1 matches the sample at n equals 1. So this shows how the power series form of x of z helps us read the time domain signal. Next, we study an example. We want to decide if a signal is right-sided or left-sided. We use the region of convergence of the z transform. We are given the z transform x of z equals this. If ROC is the magnitude of z larger than radius a, then ROC is outside the circle with radius a. We expand the expression into a power series. We get terms that look like 1. A times z to the minus 1, a squared times z to the minus 2, and so on. So this series matches x of n equals a to the n times u of n. This signal is right-sided. It exists only when n is greater than or equal to 0. If ROC is the magnitude of z smaller than a, the ROC is inside the circle with radius a. We expand the expression again. This time, the power series looks like this. Because a times z to the minus 1 is larger than 1, so we have the equation like this. The power series is minus a to the minus 1 times z, minus a to the minus 2 times z squared, and so on. This series matches the left-sided signal. So it exists only when n is less than or equal to minus 1. So the same z transform can produce a right-sided or left-sided signal. The ROC tells us which one is correct. We have learned the ROC and the inverse Z transform. We will move on to the properties of the Z transform. We studied these properties before in the Fourier transform. Now we will look at them again and see how they change in the Z transform. First, we talk about the linearity property again. We have two signals. Their Z transforms are x1 of Z and x2 of Z. Linearity means we can combine the signals. If we add and scale the signals, we have the same scaling and addition in the Z domain. Please pay attention to the region of convergence. The region of convergence for the new signal comes from the overlap of the two original regions. It is the intersection of the two ROCs, R1 and R2. If a pole and a zero cancel each other, the ROC can become larger. We can prove this property by expanding the summation in the Z transform and grouping the terms. Next, we talk about the time shifting property in the Z transform. This property helps us when a signal is delayed or shifted in time. We start with a signal x of n. Its Z transform is x of z. The region of convergence is R. If we shift the signal by n0, we write it as x of n minus n0. The Z transform becomes z to the minus n0 times x of z. The ROC stays the same. It is still R. To prove this, we replace n minus n0 with n in the summation. After we simplify it, we get the factor z to the minus n0 in front of x of z. So the time shift becomes a multiplication by z to the minus n0 in the Z domain. This property shows a delay in time adds a phase shift factor in the Z transform. For the ROC, it usually stays the same after a time shift, but we may gain or lose the point at z equals 0 or z equals infinity. If the shift amount n0 is positive, meaning we move the signal to the right, we create poles at z equals 0 and zeros at z equals infinity. These new poles or zeros may cancel the old ones. If the shift amount n0 is negative, meaning we move the signal to the left, we create zeros at z equals 0 and poles at z equals infinity. These may also cancel the old poles or zeros. So the ROC is mostly the same, except for possible changes at the origin or at infinity. Next, we look at how scaling affects a signal in the Z domain. Scaling means we multiply the signal x of n by z0 to the n. This changes its Z transform and adds its region of convergence. If x of n maps to x of z with ROC R, then multiplying by z0 to the n gives a new transform x of z over z0. The ROC becomes the magnitude of z0 times r. The proof comes from the inverse z transform. We replace the variable z over z0 with y inside the contour integral. After the change, the result shows the new signal is z0 to the n times x of n. And the new transform is x of z over z0. Now let's look at the effect on the ROC and the poles and zero. The ROC scales by the magnitude of z0. A pole or zero at z equals a moves to z equals z0 times a. So before scaling, the poles and zeros sit inside the unit circle like this. After scaling, the poles and zeros move outward or inward and also rotate by the angle omega 0. There are two cases. If z0 equals e to the j omega 0, scaling rotates all poles and zeros by omega 0. If z0 equals r0 times e to the j omega 0, scaling rotates by omega 0 and also stretches or shrink by r0. Next, we will talk about the time reversal property of the z transform. This property shows what happens when we flip a signal in time. When the signal x of n has the z transform x of z with ROCR, the time reversed signal x of minus n has this z transform. Now let's see why this is true. We start from the z transform of the time reverse signal. Here is the expression for the z transform. We change the index by letting m equals minus n. So after this change, the sum becomes this. We write the sum into the normal z transform form. So here we change this to minus m. So we can express the power of z using 1 over z. This shows the result. X of 1 over z is the z transform of x of minus m. So the time reversal changes the variable z to 1 over z. This also flips the ROC. If a point z0 is inside the ROC of x of n, then the point 1 over z0 is inside the ROC of x of minus n. So the ROC becomes 1 over r. The poles and zeros also flip. They move to reciprocal positions in the z-plane. This property is useful because it shows how the z transform reacts when we reverse a signal in time. Now we will learn about the time expansion property of the z transform. This property shows what happens when we stretch a signal in time by putting more space between its samples. For a signal x of n, the expanded signal inserts k-1 zeros between samples. So we write it like this. If the original signal has the z-transform x of z with ROCR, then after time expansion, the new z-transform becomes this, x of z to the k, and the new ROC become r to the 1 over k. This means the ROC stretches or shrinks depending on the value of k. Now let's look at why this is true. We start by writing the z-transform of the expanded signal. We change the index by letting m equals n over k. So here we have x of m. Then we get this. So we have z to the minus k times m. Now we rewrite the expansion by grouping the power as z to the k. So here we have z to the k to the minus n. This shows the result x of z to the k is the z-transform of xk of n. So time expansion also changes where the poles and zeros appear. A pole at z equals a moves to z equals a to the 1 over k. So the pattern of poles and zeros either spreads outward or move inward depending on the k. We will learn the conjugation property of the z-transform. This property tells us how taking the complex conjugate of a signal in the time domain affects its z-transform. Suppose we have a signal x of n, and its z-transform is x of z with ROCR. If we take the conjugate of this signal, written as x star of n, then the z-transform becomes the conjugate of x star of z star. The region of convergence stays the same. So when we take the z-transform of x star of n, we take the conjugate of every term in the summation, including the z to the minus n term. So we have this. If we then replace z by z star, we see the result become the conjugate of x of z star. So the conjugate in time maps directly to the conjugate in the z domain. There is one special case. If the signal x of n is real, then it equals its own conjugate. That means x of n equals x star of n. So x of z equals x star of z star. The z-transform has conjugate symmetry. Poles and zeros also follow this rule. If x of n has a pole or a zero at z equals z0, then it must also have one at z equals z0 star. We already saw an example earlier. For this signal, its z-transform has a pair of conjugate poles like this. So if there is a pole at 1 over 3 e to the j pi over 4, there must also be a pole at this location too. This is the conjugate property in the z-transform. In this slide, we will learn the convolution property of the z-transform. This property tells us one key idea again. convolution in time becomes multiplication in the z-domain. First, think about two signals. One signal is x1 of n, and its z-transform is x1 of z with ROC R1. The other signal is x2 of n, and its z-transform is x2 of z with ROC R2. When we convolve these two signals in the time domain, the result in the z-domain is very simple. We just multiply their z-transforms. So the z-transform of the output is the product of x1 and x2. For the ROC, it must include at least the overlap of the two original ROCs. If some poles and zeros cancel, the ROC can become larger. Now let's look at an LTI system example. The output y of n is the convolution of the input and the impulse response. The impulse response here is the simple difference of two impulses. This impulse response takes the current sample and subtracts the previous sample. In the z-domain, this impulse response becomes a simple expression, 1 minus a delay term. So if the input signal has z-transform x of z with ROC R, then the output is obtained by multiplying x of z with the system's z-transform. Back in the time domain, the convolution result is also easy to understand. The output equals the current input minus the previous input. So the output z-transform is the system function 1 minus z to the minus 1 times the input z-transform. The ROC of the output is usually the same as the input ROC. However, there can be small changes. Sometimes the origin may be removed, or a new point z equals 1 may be added because there is a pole. So depending on the pole zero cancellation, we might have new ROC. This example shows how convolution in time becomes multiplication in the z-domain. In this slide, we will learn about the differentiation property of the z-transform. This property helps us analyze signals that involve change, such as trends, growth, and rate-related behavior. We start with a signal x of n and its z-transform x of z. Now think about multiplying the signal by the index n in the time domain. This operation does not stay as multiplication in the z-domain. Instead, something important happens. Multiplying the signal by n in time becomes differentiation in the z-domain. We begin the proof from the basic definition of the z-transform. Then we take a derivative of the z-transform with respect to z. So when we do this, the index n naturally appears from the power of z. So after simplifying, we see a clear result. The effect of multiplying by n in time is the same as taking a derivative of x of z and scaling it by minus z. So the key takeaway is simple. Time domain multiplication by n turns into differentiation in the z domain. This property is very useful when analyzing systems related to change or dynamics. Now let's see this example. We need to find the inverse z transform of a logarithmic function. We are given x of n as the log of 1 plus a times z to the minus 1. The ROC is outside the circle with radius a. First, we use a known z transform property. Multiplying x of n by n in time corresponds to differentiation in the z domain. So we take the derivative of x of z. After differentiation, we get a simple rational form. This form matches a standard z transform pair. From the table, 1 over 1 plus a times z to the minus 1 corresponds to minus a to the power of n times the unit step. Next, we apply the time shifting property. Multiplying by z to the minus 1 means a delay of one sample. So the signal becomes minus a to the n minus 1 times the unit step shifted by 1. Now we combine the results. The final time domain signal y of n is a times minus a to the power n minus 1 multiplied by the unit step at n minus 1. So finally, we divide by n to recover x of n. This gives the inverse z transform result. This example shows how differentiation and time shifting help invert a logarithmic z transform. This table summarizes the main properties of the z transform. Each row shows how a change in the time domain signal affects the z domain expression. Time shifting in the time domain adds a power of z to the minus 1. This is one of the most useful properties. Time reversal replaces z with 1 over z and inverts the ROC. Time expansion increases the spacing between samples, replaces z with z to the k. Convolution in time becomes multiplication in the z domain. Multiplying signal by n in time corresponds to differentiation with respect to z. These properties help us analyze discrete time signals and systems efficiency using the z transform. This table shows the basic z transforms of common discrete time signals. It lists signals such as the unit impulse, unit step, exponentials, and shifted sequence. The table also shows how the region of convergence depends on whether the signal is right-sided, left-sided, or two-sided. The basic z-transform pairs are the building blocks for solving many discrete time signal and system problems. In this slide, we move from the properties of the z-transform to the analysis of discrete time, linear time invariant systems. The Z-transform is a powerful tool. It helps us study causality, stability, and systems described by linear constant coefficient difference equations. This figure shows how the input signal x of n goes through the system. The system has an impulse response h of n in the time domain. In the z domain, the system is represented by the system function h of z. We multiply x of z by h of z to get y of z. This gives the output signal in the z domain. The z domain helps us move from signal analysis to system analysis. It helps us check whether a system is causal or stable. It also helps us understand how the system responds to any input signal. Do you still remember the definition of a causal system from Chapter 2? A causal system has an impulse response that is zero for all negative n. A stable system has an impulse response whose absolute sum over all n is finite. In this slide, we talk about causality in the Z-transform. Causality tells us whether the output depends only on the present input and past input. A discrete time system is causal if the impulse response is zero for all negative time. That means h of n equals 0 for negative n. So the impulse response is a right-sided signal. The system does not respond before the input happens. Because h of n is right-sided, the ROC of h of z must be the exterior of a circle, and it must include z equals infinity. So if h of z is a rational function, then causality has two simple rules. First, the system is causal if and only if the ROC of h of z is outside the outermost pole. The ROC is the exterior of a circle that lies beyond the largest pole magnitude. Also, for a causal rational system, h of z equals n over d. The order of n of z must be less than or equal to the order of d of z. This condition makes sure that h of z stays finite when z equals infinity. Causality is very important for real-time systems. A real-time system can only use present and past inputs, not future ones. The ROC by itself cannot fully determine causality, but it must match the form of h of z and the fact that h of n is the right-sided signal. In this slide, we look at an example of causality in the Z-transform. We are given a system function h of z. It is written as the sum of two simple terms. The ROC is outside the circle with radius 2. First, we find the poles. The poles are at 1, half, and at 2. Next, we check the ROC. The ROC is outside the outermost pole, the pole at 2. This matches the condition for a causal system. Then we rewrite h of z as a ratio of two polynomials. From this form, we can see the order of the numerator is not higher than the order of denominator. This means h of z is finite at infinity. So the system is causal. Finally, we look at the impulse response h of n. The impulse response is the sum of two right-sided exponentials. Because h of n is right-sided, this again confirms the system is causal. Now we talk about stability. Stability means the system output does not blow up. In time domain, this means the impulse response can be added up in magnitude. In frequency terms, this also means the Fourier transform exists. In the z domain, this means the ROC must include the unit circle, the circle with radius 1. Now, let's look at the figure. For the left figure, the shaded blue area represents the ROC. The solid black circle is the unit circle. The unit circle is fully inside the ROC. Even though there are poles inside, the unit circle is still covered, so the system is stable. For the middle figure, the ROC is inside the dashed circle. The unit circle is inside the ROC. The Fourier transform exists, so the system is stable. For a causal and stable system, all poles lie inside the unit circle. The ROC extends outward and includes the unit circle. This satisfies both causality and stability, so this system is stable and causal. So stability needs the unit circle inside the ROC. For a causal and rational system, stability means all poles are inside the unit circle. In this example, let's look at one system and see how the ROC changes the system behavior. We are given a system function with two poles. One pole is inside the unit circle, and one pole is outside the unit circle. So the system behavior depends completely on the ROC. First case, if the ROC is outside the outermost pole, so outside radius 2, this ROC does not include the unit circle. In this case, the impulse response is right-sided, so the system is causal. But because the unit circle is not inside the ROC, the system is not stable. So this system is causal but not stable. Second case, if the ROC is inside the innermost pole, so inside radius 1/2. Again, the unit circle is not included. Now the impulse response is left-sided, so the system is not causal. And because the unit circle still not in the ROC, the system is also not stable. So the system is neither causal nor stable. Third case, if the ROC lies between the two poles, between 1/2 and 2, like this, this ROC does include the unit circle, so the system is stable. But the impulse response is two-sided, so the system is not causal. So in this case, the system is stable but not causal. This example shows an important point. Causality and stability depend on the ROC, not just the poles. In this example, we look at a second-order system in the Z-domain. The system has two poles. They form a complex conjugate pair. One pole is at radius r with angle theta. The other pole is also at radius r, but with angle minus theta. You can see the two poles marked symmetrically around the real axis. They are both on a circle with radius r. If the system is causal, the ROC is outside the circle with radius r. This means the shaded region is outside the pole circle. Now we check stability. A system is stable only if the unit circle is inside the ROC. So if r is smaller than 1, the poles are inside the unit circle. The ROC is outside the poles and includes the unit circle, so the system is causal and stable. But if r is larger than 1, the poles are outside the unit circle. The ROC is still outside the poles, but now it does not include the unit circle, so the system is causal but unstable. So the key idea is simple. For a causal system, stability depends on whether the poles are inside the unit circle. Next, we talk about linear constant coefficient difference equations. These equations describe a discrete time system by linking the input and the output. The difference equation has delayed versions of the output on the left side. Each delayed output has a coefficient ak. The right side has delayed version of the input, also with coefficients bk. This form shows how the current output depends on past output and past input. To study the system, we take the Z transform. Each time shift becomes a power of Z inverse. This turns the difference equation into an equation in the Z transform. The system function is the output transform divided by the input transform. It becomes a ratio of two polynomials in Z inverse. The zeros come from the roots of the numerator. The poles come from the roots of the denominator. Poles and zeros control stability and frequency response. So we turn a difference equation into a simple Z-domain expression using the Z transform. This makes analysis much easier. Engineers use this method in digital signal processing, control systems, and digital filters. In this example, we want to find the system function of an LTI system. We are given the input signal x of n. The input is a decaying exponential. It starts at n equals 0, so it is a right-sided signal. We are also given the output signal y of n. The output is a sum of two decaying exponentials. Both terms are multiplied by the unit step, so the output is also right-sided. Next, we take the z transform. For the input, we use the standard exponential pair. The result is a simple form with one pole. The region of convergence is outside a small circle. For the output, we transform each exponential term. Then we add them together. After simplification, the result becomes one rational function. The region of convergence is outside the larger pole. Now we find the system function h of z. For an LTI system, the system function is the output transform divided by the input transform. So we take the ratio of the two results. After cancellation and simplification, we get the final form of the system function. Finally, we look at the region of convergence. The system is right-sided, so it is causal. The region of convergence is outside the outermost pole. It also includes the unit circle. That means the system is stable. So the final conclusion is simple. This system is causal and stable. In this example, we study a system that is stable and causal. We are told several facts about the system. The system function is rational. There is a pole at 1/2. There is a 0 on the unit circle. From what I see, the ROC looks like this. Now we check each statement one by one. First question, we look at the Fourier transform of the impulse response multiplied by 1/2 to the power n. The Fourier transform of this is the same as evaluating h of z on the circle where r equals 2. It will converge only if this circle is inside the ROC of h of z. We check if r equals 2 is inside the ROC. Because the ROC must be outside the pole at 1/2, r equals 2 is in the ROC, so the statement is true. Second question, we ask if the frequency response is 0 as on frequency. We are told there is a 0 on the unit circle. That means the frequency response becomes 0 at that point. So this statement is true. Third question, we ask if the impulse response has finite duration. A finite duration signal needs a region of convergence that covers almost the whole z-plane. But this system has a pole at 1/2. So the region of convergence cannot be the whole plane. This means the impulse response is not finite in length. So this statement is false. Fourth question, we ask if the impulse response is real. For a real signal, poles and zeros must appear in complex conjugate pairs. We are not given this information, so we cannot decide. There is not enough information. Fifth question. We define a new signal. We convolve the impulse response with itself. Then we multiply by n. Convolution in time becomes multiplication in the z-domain. And multiplying by n becomes differentiation in the z-domain. These operations does not move the unit circle from the region of convergence. The unit circle is still included, so the new system is still stable. This statement is true. Please remember that sometimes there are things we cannot decide. There's not enough information. Just like this. To help you understand these ideas better, please practice the questions from Chapter 10. Try to solve them by yourself. Think step by step and try different ways. This will help you understand the concept better. After you try, you can check the solution manual. These topics will also appear in the final exam, so please review carefully.